This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Anaban runs to a tree 2 meters north of his starting location, then runs to a spot 4 meters south and 8 meters west of his starting location. How far did he run? We will assume Anaban is running on a plane instead of on a sphere. Then we simply draw a diagram. This is his starting location here. First he runs 2 meters north to this point here. Then he runs to a spot 4 meters south and 8 meters west of his starting location. So he starts here, runs to here, then he runs down here. And the question is asking, how far did he run? Denote the length of the red line by x, then clearly he ran 2 plus x. So we just have to determine x. We have a right angle triangle here, so Pythagoras' theorem applies. 8 squared plus 6 squared equals x squared. That tells us that x is 10 and therefore he ran 12 meters. If we pick a right angle triangle at random, then in general we are not going to get integer side lengths. If you do get integer side lengths, then the 3 side lengths are known as a Pythagorean triple. In our case, the triangle we had was 6, 8, 10. And if we divide by 2, we get 3, 4, 5, which is, if you like, the basic example of a Pythagorean triple. Are there other examples of Pythagorean triples? Can we find all of them? Often it is easier to work with rational numbers than with integers. Roughly speaking, rational numbers have stronger properties than integer numbers. In particular, you can always divide 2 rational numbers and get a rational number, whereas with integers, most of the time if you divide 2 integers, you do not get an integer. Technically, rational numbers form an algebraic field, while integers only form an algebraic ring. If we find a right angle triangle which has got rational lengths, then we just have to multiply by a sufficiently large integer to clear the denominators and get an example of a Pythagorean triple. Therefore, we can ask the question, how can we find all rational examples of Pythagorean triples? It suffices to find all rational examples up to scale, so we assume that the hypotenuse has got length 1. In this diagram then, we want the point AB on the circle to have rational coordinates. Here A is the length of this side and B is the length of this side, and that corresponds to a point specified by its xy pair, so to speak, A, B. From this diagram, we see that finding a triangle with rational lengths is the same as finding points on the unit circle with rational coordinates. The 2 problems are equivalent. Finding all right angle triangles with rational side lengths up to scale is identical to the problem of finding all points on the unit circle with rational coordinates. Indeed, given a triangle, a right angle triangle with rational coordinates, we just have to divide all sides by the length of the hypotenuse. It can then be drawn precisely in this diagram, and since its lengths are rational, in particular A and B are both rational, it corresponds to a point on the unit circle with rational coordinates. If we had a rational parametrization of our unit circle, we could answer this question. And on the 10th of January, we indeed discussed a rational parametrization of the unit circle. Recall that on the 10th of January we introduced this diagram here, we have the point over here at -1, 0. We have the unit circle. We pick a point T on the vertical axis and we draw a line from -1, 0 through T and look to see where it strikes the circle a second time. We then get a right angle triangle as such, and we showed on the 10th of January that the coordinate of this point here was precisely 1 minus t squared on 1 plus t squared, comma 2t on 1 plus t squared. If t is a rational number, then both these numbers are also rational. Remember, rational numbers form an algebraic field, so we can add them, subtract them, multiply them, and divide by anything other than 0, and we will still get a rational number. Because this is a unit circle, we can draw a line from the origin to this point here, and that's got length 1. This right angle triangle has got height given by 2t on 1 plus t squared, and the base length is 1 minus t squared on 1 plus t squared. We therefore have a right angle triangle, all sides of which have got a rational length. We have therefore found a rational example. Redrawing it here with the side lengths flipped, we can clear denominators by multiplying all side lengths by 1 plus t squared. That will give us 1 plus t squared along the hypotenuse, 2t along here, and 1 minus t squared along here. Any rational value of t will give us a triangle with rational lengths. Technically, if a side length ends up being negative, we just take its absolute value. We'll return to this point presently. By way of example, if we choose t to be 1/2, which is a rational number, and substitute that in, we get a triangle with side lengths 1, 3/4, and 5/4, which, when we multiply by 4 to clear denominators, gives us our 3, 4, 5 triangle. We could also choose t to be equal to 2, in which case we would get 5 here, 4 here, and the -3 here, which would simply mean in this diagram here the triangle's gone to the other side. The -3 we replace with 3. We therefore get our 3, 4, 5 triangle back again. Different values of t may or may not give us different triangles, and we can ask the question, can we get all rational triangles in this way? Previously, we saw that the two questions of finding rational examples and finding rational points on the circle were equivalent questions, but now we have a rational parametrization, and we need to check that if we find a rational point on the circle, then t itself will be rational. To show we can find all Pythagorean triples up to scale in this way, assume we have a Pythagorean triple here. C squared equals A squared plus B squared. Tangentially, if C squared equals A squared plus B squared, then the triangle is guaranteed to be a right angle triangle. That result is the converse to the Pythagorean theorem, and it means that we have another equivalence of questions. Finding all Pythagorean triples is equivalent to finding all integer solutions to c squared equals a squared plus b squared. A reminder that whether we require a, b, c here to be integers or rational numbers makes no difference. On the one hand, we just want to find all Pythagorean triples with a, b and c being integers, so it would make sense to restrict a, b and c here to being integers. Yet on the other hand, there's an equivalence between integer solutions and rational solutions. Given any rational solution, we can clear denominators and get an integer solution. If this method gives us all rational solutions, then a fortiori we get all integer solutions, since we are allowed to scale. In what follows, we don't need to use the fact that a, b and c are integers, only that they are rational. Therefore, we may as well assume a, b and c are rational to start off with. Given a, b and c, we shrink this triangle by dividing all side lengths by c. That makes the hypotenuse have unit length, and it can therefore be drawn so that this point lies on the unit circle. The coordinate of this point here is precisely a on c, b on c. Since a, b and c are all rational, then the coordinates of this point are also rational. The question then is whether t is itself rational. Remember, we found all points on the unit circle for which t is rational. So if we want to find this particular point, which gives us this particular triangle, then we need t here to be rational. Given the coordinates of this point here, how do we find t? Well, t is simply the slope of this line here, its gradient. And so we simply have to look at rise over run. This tells us that t is equal to, well, the rise is how high up we've gone, which is going to be b on c, and the run is the distance from here to here, and that's going to be 1 plus a on c. Another way of saying this is we're just using similar triangles. The smaller triangle here has got a base length of 1, height of t, and we have a bigger triangle here. And so if we want to find the height of the smaller triangle, then we just have to take the height of the bigger triangle and divide by the appropriate scaling factor. In this case, the larger triangle has got a base of 1 plus a on c, and the smaller one has a base of 1, so this gives us the scaling factor we require. We therefore see that t is equal to, in terms of the coordinates here, it's equal to b divided by a plus c. So if a, b and c are rational, then t is rational, and therefore we will find this triangle using our rational parametrization from before. This is not the most efficient way of finding all Pythagorean triples, but it is certainly one way of doing it.